question? So there was an argument with after the class. Someone else, I think it was Tadeo, about exactness. I claimed I seem to have been claiming that the functor was additive for an abelian category for free, and it's not. I just require functors on abelian categories. Whenever I talk to functors between abelian categories, there are going to be additive. Or in other words, you require them, in the case of exactness, to preserve this limit that was the direct sum. But anyway, so I want to have examples, remember what adjoint functors were, and I want to have some examples of adjoint functors. And I only know one. So if you know other examples, tell me, and then we can work them out. But I only know one example of adjoint functor. And essentially it goes to this, and it has several flavors of the same thing. So let's first look at the category of R modules. And let's take R to be a commutative ring. So we have the following functor. So let's say that you have a module M, which is an R module. Then we have the functor hom from M dot. So this is in the category of R modules. And well, you can take this functor as a functor from the category of R modules, just as abelian groups. But if you give me two modules over a commutative ring, then the set of homomorphism of R modules between those two modules is also an R module. So this happens to be an R module. And this functor is left exact. So it's additive, that's clear, and it preserves kernels. So if I have a sequence of modules, say K to N to P, I'm just choosing random names. And I look at maps from M to K, then I can compose with this map to get a map from M to N. So if I give you an element of hom mk, the composition by I gives me an element hom mn, and the composition by F gives me an element hom np. So let's analyze that composition. So the composition by I is this. Is a map from hom mk to hom mn, and I is injective. So if there's anything in the kernel of this map, that means that for every element in M, phi composed with I of M is equal to 0. Oops, the other way around. I of M is equal to 0. But I is injective. So phi of M is in the kernel of I, which is 0. Therefore, M is equal to 0. So that means that phi, the kernel of this map, of this composition by I, is 0. So it means that this map is injective. On the other hand, let's suppose that we take now phi in hom m n such that the composition of f with phi, I guess like this, so this is 0 inside of hom mp. So that means phi is in the kernel of the composition by f, which is a map from here to here. And I take phi in the kernel there. All right? So if this happens, then that means that f of phi of m is equal to 0 for every m, same argument. And this means that phi of m is in the kernel of f for every m. But the kernel of f, since this sequence was exact, is the image of I. So this means that phi of m is in the image of I for every m, so that I can always choose an element, I guess k, in k, such that phi of m is equal to I of k. So what I'm saying is that the image of phi that goes from m to n factors through the image of a map from m to k. So I can take phi bar that grabs m and it gives me k. And you can make this into a map of R modules. So phi happens to be in the image of phi bar. Oops, phi is the composition of I with phi bar. So in other words, the kernel of the map from hom mn to hom mp is the image of the composition by I. So what we get is this exact sequence. We've proven that this map is exact, is injective, and that this sequence is exact here. And of course, this is no longer not exact at the last step. And you get to check that. So check that is not necessarily exact at start or here at this point. Namely that the last arrow is not a surjection, might not be a surjection. So modules let's define that later. We'll talk about this in a second. All right. So a module such that whenever you give me a map to P, you can lift it by n. It's going to be called a projective module. All right. So another functor that you have on the category of R modules is the tensor product with that. So we get a functor that is the functor tensoring with L over the ring R. And this one is right exact. Right exact. In the sense that if you have the same exact sequence that we have there, I think I named them, that's a problem of choosing random letters, K and P. K and P. Then you can take P tensor with L, N tensor with L, K tensor with L, and now this sequence is exact. And this one is constructed just if I call this F and I as before, then this map here sends N tensor L to F of N tensor L. And extend that linearly. Now F is a surjection. An element here is a linear combination of things of the form P tensor L's with P in P and L in L. And, well, you can always find preimages of this piece because F was rejected. So choose P bar. So choose F of P bar equal to P, and then take the sum of these guys, tensor the same L's. Oops, sorry. So here this P bar is in N. Probably I should have used the letter N, but anyways. So apply F to this thing. Apply this map to this thing, and you get just your sum of P tensor L's. So this linear combination, which is in N tensor L, is clearly in the preimage of this map. So this guy preserves surjections. And the same argument you use for exactness at this point. So if you look at something that gets sent to 0 here, then you can choose preimages of the first factors in each one of the linear combinations that you chose because of exactness of this sequence. And therefore, you've checked that this sequence is still exact at this point, but it's not exact at this point. So try to find an example of a module L that makes it, that does not preserve the first injection. That's a kind of, it's very simple to find modules L that will not, and sequences like this that are not going to be exact at this thing. You just take a module that is pure torsion for the ring. All right, so we have these two functors. And they are adjoint in a sense, which is this, for every 3 modules. And this is perhaps the defining property of the tensor product. So examples for M, N, and P in our modules. We have natural isomorphisms from the morphisms, the set of morphisms between M tensor N and P, and the set of morphisms between M and Homs NP. Now this is an R module, so I'm going to write this underline here to remember that this is an R module. Well, actually, this happens at at the level of R modules, but yeah, so let's use this as an R module. And now this isomorphism is an isomorphism of R modules, but it's good enough that it is an isomorphism of sets, which is what I required for 2 functors to be adjoint. So we see here that I can view this as maps from the functor tensoring with N applied to M. So this is the functor tensor with N applied to M to P. And this is in the category of R modules. This functor tensoring with N is this. So tensoring with N applied to P, I define it to be that functor, N tensor P. So that's this. And on this side, I have Hom from M to the functor Hom with N applied to what? This is, let's put a different name now. Hn applied to P. Here the functor Hn applied to P is the functor Hom NP, the category of R module. And I'm viewing this guy as an R module, not only as a set. So this is natural. This is a natural isomorphism. This isomorphism is what? It sends, suppose that you give me a morphism like this. So you have some phi that lives here. And you want to get a map here. So what is the image of this? Under this isomorphism, let's call this I small. Under this isomorphism, this phi goes to a map here. What is that map? It takes n, and it needs to give you an homomorphism between n and p. So that homomorphism would grab n and map it to phi of m tensor n. So you can check all the compatibilities of those two functors. I'm surprised no one complained yet, but I'm waiting to hear a complaint. And so I won't stop until someone complains here. But what you get is therefore that the functor tensoring with n is left adjoint. And of course, I forget if I was using this symbol or the other one, but it's on the left. And I have the other guy on the right, so this is 2hn. Okay. So that was the definition of being for two functors to be in a joint, that if I apply one on one side, it's naturally isomorphic to applying the other one on the other side of the home. And I've mentioned a theorem that said that if I have these adjunctions, then, so this was a general theorem, and this is an evidence for that theorem. General theorem was that if I have two functors, f to c and g from d to c, between two categories, and f is left adjoint to g. Again, I never remember the symbol, but this is on the left. This is a left adjoint to g. Then f is right exact, and g is left exact. Which indeed happens in this case. We checked right exactness for the tensor functor and left exactness for the home functor. So we get that for free by knowing that they are adjoint. So that's just as evidence for this theorem that we need to prove in a second. Okay, so this is the only example that I know of a pair of adjoint functors. But let me show in a subtle example. Again, someone should complain about that board. I'm going to erase it at some point, and if no one complained, I'm going to leave it at that. Or at least, if no one is complaining, then at least someone should try to find the inverse to see if there's an issue in what I said. So I've given you the map from here to here, and I'm claiming these two guys are isomorphic. So I'll let you think whether or not I need to add adjectives to this module so that this actually becomes true. But try to find an inverse map to that. All right. So here's another example of the same. I'm going to give the same example in a different way. Let's take G to be a group. But for a little bit, we can take it to be finite. So if you're happy, just take it to be finite. A finite group. It's not needed for what I'm going to say now. Remember in general what a representation of a group is? A representation of G is a map of groups from G to GL of some vector space. An homomorphism of groups. And these are linear, invertible linear endomorphisms of a vector space. So any homomorphism of groups like this is called a representation of the group G. Okay? Now, of course, if you have a subgroup H of G, you have a functor which is just from the representations of G to the representation of H, which just forgets the action of the whole of G and only remembers the action of H. Namely, we have a category of G modules. These are representations of G. And we have a category of H modules. These are representations of H. If you give me a homomorphism of groups from G to GLV, here, you can compose with the inclusion of H in G. You obtain a homomorphism which goes from H to G by the inclusion, and then compose with this homomorphism here to GLV. You just only remember this composition, and that's an homomorphism of groups. So that sends representations of G to representations of H. Okay? This is a functor. Namely, if you have, so I need to define the category of representations of G. What is a morphism between two representations? So if you have rho from G, well, I have it here, rho from G to GLV, and you have some eta from G to GLW, then a map between these two representations, an homomorphism of representations, of G modules. This is a linear map as a linear map between V and W, such that it intertwines the two representations, namely it takes, well, it takes rho of G. This is an endomorphism of V. And then I can apply S. And now this is a map that goes from V to W. Or I could apply S to an element in V, and then apply eta of G. And this is equal for every G in the group. So that's the definition of a homomorphism of representations. The set of these guys, I'm going to denote hom G VW. And I'll forget the notation of rho and eta. I just have a vector space V where G acts, a vector space W where G acts, and a morphism, a linear morphism commuting with the action of G is an homomorphism. If you have this situation, of course, this maps by only remembering the H actions to an homomorphism of representations of H. So this functor is very simple. The question is, how do I construct a functor in this direction? And the point is that there's a few different ways of doing this. Well, there's at least two ways of constructing a functor from here to here. So, question, given an H module, how do I construct a G module? Okay. So there's a couple of ways that I can think of. So suppose that you give me an H module. Let's call that H module V. Okay? So we have a map now, rho from H to GLV. And what I would want is to extend this action to the whole of G somehow in this vector space V. Okay? One thing you can do is look at the set of functions. Functions from H to V. Oops, sorry, from G to V. Now, the group H acts on G, and the group H acts on V as well. So this is going to be the set of functions from G to V that are compatible with the action So how can we put that compatibility condition? So again, someone has a complaint about this board? No one has complained? No one finds anything fishy here? I've claimed this isomorphism. No one complains about this? Okay, I'll leave it to you. I'll come back to this isomorphism in a bit. All right, so what kind of compatibility conditions can I impose here? And yeah, it depends on where do we want to get an action in the end, but what I claim is that H acts, and it acts in several ways on G. It acts in only one way on V. So the action on V is clear what it is. If you give me an element H in the group H and a vector V in the vector space V, then we can define the action of H and V by just rho of H applied, evaluated at V. So there's no choice for that. We're given a representation this way. But on G, we can act in different ways. On G, I can act on the right by multiplication, on the left by multiplication, by conjugation by H. So there's a bunch of different actions that I can choose on G. Okay, so what are conditions of compatibility that I may want to look at? Well, I can require, for example, that if you give me H and you act this, oops, oh, sorry. So that's a function from G to V. So this is an element in G. Therefore, f of this is an element in V. And let me put this in the other way. And you can require that this is H acting on V, on f of G. And you require this for every H in H, G in G. That's one compatibility that you can ask for. Okay, so now this is a vector space. If you take two functions that satisfy that identity, the sum of them obviously satisfies the same identity. A multiplication by a scalar guy also obviously satisfies this identity. So this is a vector space, and this is the compatibility means this equation. Well, this is one of them that I can choose. I can choose different ones. And the question is, do I have an action of A of G in this space? So if you give me a function satisfying these conditions and an element G in the group, in the bigger group G, how can I possibly define something like G acting on F? This should be a new function from G to H, from G to V, that should still be compatible with the action of H. Can anyone guess? So I want to understand how to give a new function. And now here I'm going to evaluate this in some G prime. And I should get a vector in V. I mean, of course, you can just take the trivial action. But that's not good enough. So I would want to restrict. This should give me a representation of G such that when I restrict it to H, I should get my original representation. So what can I do? So I can do f of G prime times the inverse of G. Okay, so that's at least an element in V. Is there any other guess? So let's check if this still satisfies this condition. So this is my definition of this function. So I grab G acting on F, and I multiplied by h g prime, and I see that this is, by this definition, is f of h g prime g inverse. Now, the group is associative, so putting the parentheses here is the same thing as f of h g prime g inverse. And the function f was compatible, so f of h times something is the same thing as h times f of something, which in this case is g prime g inverse. And this is h acting on g times the function evaluated at g prime, which is exactly what we wanted to check. So this is a function that is still compatible with h. So this is at least is an operation that goes from the vector space, this vector space, so we're going to put a name to this vector space in a little bit, to itself. And it's a linear operation. Namely, if you take the sum of two functions, clearly this goes to the sum of those functions. If I multiply this function by a scalar, this goes to the same scalar, multiplication by the same scalar. So this is a linear operation. So this is a map from G to GL of this vector space. Let's check there is an action. Right? I needed my map to be a representation should be a morphism of groups from G to GL of that vector space. So I need to check. I need to check that if I grab yet another guy, that's G, it's a bad idea. I don't want to keep accumulating G's and G primes, and let's just choose a different element. Let's say, yeah, I can't think of a name, so I'm going to take G tilde. Acting on G, acting on F. And I want to see what this function is evaluated at an element G prime. Now, by definition of this, this is G tilde acting on this function evaluated at G prime. So this is this function, G times F, on G tilde times on G prime times G tilde inverse. That's the definition I was just given. And now, by the definition of this guy, this is F on G prime, G tilde inverse, G inverse, which is F of, again, associativity in the group, G tilde inverse, G inverse. And now the fact that taking an inverse is an anti-involution of the group, this is G tilde times G tilde. I keep saying tilde when it's primed. Inverse, and this is the same thing as G times G tilde acting on the function F evaluated at G prime. And this is true for every G prime. This implies that G tilde acting on G acting on F is equal to G tilde acting on F, which is not quite good. This is an action, but this is an action on the right. And if I have this morphism, this is an action on the left, on the vector space V. So this seems to be not a morphism from G to GLV, but it's a morphism from the opposite group of G to GLV. Is that right? Is that right? You seem to be worried, Bruno. Did I screw up somewhere? So we can fix this, and we can fix it how? I could, for example, have avoided this inverse here. And if I avoided that inverse there, it wouldn't be there. Then it wouldn't be here. Then it wouldn't be here. And then same thing would have happened here. So it still would have been a compatible function. If I didn't have that inverse, then everything would be fine here. If I didn't have that inverse, then this wouldn't be here, this wouldn't be here, this wouldn't be here, this wouldn't be here, this wouldn't be here either. And here I stopped, well, these two would exchange, and I would have a good action. So I can do that and just get a good action. Or another thing I could do is shift the action of H on the other side, use compatibility with the action of H on the right, now for G, and then use this action on the other side. I'll just keep this because we already wrote everything, so I'll define that representation. But then, so let's keep this, let's avoid the inverse. This is an action, now this became an action instead of an anti-involution. So we have a map from G to GL of that vector space. Okay, and just to be very, very clear, we have a map from G to GL. I don't want to give a name to this space yet, but it's GL of the space of these functions from G to V compatible with H that satisfying star. And star is this equation that we have here. And this map just takes an element G in here, a function f here, and it gives you the new function that evaluated on G prime is f of G primes times G. Okay. So now, I can restrict, this is a representation, so I can restrict it to my H. And certainly, this is not the original representation that I had. So if I restrict the restriction functor from this representation to H is not the representation I started with. It's kind of clear, right? Because this space is much larger than the space V that I started with. Many, many more functions from G to V, unless G is trivial, and H is trivial, than the vector space V that I started with. So it's a larger space. Okay, so let me call this. So I have now two functors. I've produced explicitly two functors. Let me call this functor co-induction. I may want to change, and I'm going to get isomorphic objects, but I may want to change here this H acting on the other side and G acting on this side. But those are minor things. The point is that this is a functor, co-induction. I'm going to put G and H on the top. And this is a functor that goes from H modules to G modules. You give me an H module. I construct all the functions from G to that H module V, and this comes with an action of G. And that action is very natural. It acts like the multiplication of G on itself. Okay. Let me give you another one that you might be more used to. You've seen these things before. So let's cook up. So here the trick we've used is we're using our representation V. We are using our group G, and this is a set where G acts by itself, by multiplication. So we're using that action by multiplication to construct the G module structure on the space of functions. So now let's do something different, which is let's cook up a big representation of G and of H at the same time. So take the following. Take K of G, and this may depend what this guy is on what kind of group you start with. So if you start with a finite group, this is going to be a very simple object. This is just the direct sum for G in G of a copy of G, and you put, this is just a symbol, E sub G. So you take one copy of the field. So this is a vector space of dimension, the number of elements of G. So this is a K vector space of the dimension the number of elements in G. And you can view this guy as an algebra with the multiplication EG times E G prime. You define it to be E of G times G prime. And the unit is E times the 1 in the group. That's the unit for this algebra. So this is an associative unital algebra. This is an associative unital. And it's not commutative unless the group G is commutative itself. Algebra. It's called the group algebra of G. Which is called the group algebra of G. If G is not finite, then, well, we might want to do something else. And what we do depends on the group. So if G is compact, for example, if G is compact, can anyone guess what sort of object should I take when G is compact? Fala más fuerte. L2. So I don't really know what this is, but this sounds correct. I would want to take L1 functions. So whatever this is, that I don't want to get into that, it's some notion of integral on my compact group. So some notion of measure. And let's see what is the structure that I want to take. So what I will take is going to be functions on G in some way, just as here. Here, these were functions on G. You could take V to be the trivial representation of H, and it's going to be functions of G to the field, which is exactly what we're doing there. So here you can view this as functions on G. It's just that this is the dual to functions on G. So here's something that you can always do whenever you have an operation on a set. So we have G, and we have two projections to G, and a third projection to G. These two, I'm drawing them here. We call this pi 1, pi 2, and this is the multiplication. Let me call it M to be the multiplication. There's something very simple to do from functions in G. Now I'm going to use this generic letter, O of G. This will mean functions in G, whatever you want these functions to be. And by whatever I mean something like this. If G is finite, any function. G is finite, it means any function from G to the field. If G is compact, you may want to take continuous functions. We'll fix this in a second. If G is algebraic, it's an algebraic variety with a multiplication which makes it into a group in the category of algebraic varieties, you'll take algebraic functions. You'll take algebraic functions. So the beauty of functions is that whatever category you choose, you can compose. This map, first of all, is going to be a map in the appropriate category. If you're talking about finite groups, this product here is going to be a finite set, and this is a map of finite sets. If G is compact, the product is compact, and this is still a continuous map, it's a proper map. So whatever this guy is a nice map. Both projections are very nice. And if you give me a function in O of G, you can pull it back. And I'm going to call this guy pi lower star of f, and this is just simply the composition of f with pi 1. So this is just apply f and compose with pi 1. If you give me a function from G to the field, you obtain a function on the product by mapping first to G and then compose with your function f. So this pullback is a function on G cross G. If you give me another function, I'm going to use G is a bad idea. Let's use H, a function in OG. You now can pull it back by pi 2. And now this is both of these guys are functions on G times G. Okay? So now I have two functions in G times G. I can multiply them in G times G. So I can look at pi 1 lower star of f. Again, this is just f composed with pi 1. Pi 2 lower upper star of h. Multiply them. This is the multiplication of usual functions. Multiplication in G times G. So now this is a function in G times G. And what I want is a function in G. So now I want to define something like this. And this is where the trick is of L2 that you have in mind. So I need to somehow tell you how to construct a function in G when I have a function in G times G. And here the multiplication of G should appear, and this should model that algebra that I wrote there. I mean, this algebra here, the multiplication in this algebra depends on the multiplication in G. The multiplication in the space of functions on G does not. This only depends on the structure of the field, K. So at some point I need to use this map M, which is the multiplication of G, and it's going to be here in the definition of this push forward. Okay? And that definition is going to depend on what kind of group you are. So let me do this for finite, and it's going to be clear what's going to have to become to be for compact or not. So if you have a function, what do I need to construct a function here given an arbitrary map? Now I can just take maps. So let's suppose that I have x, and I have y, and I have a map M between these two, and x and y are finite sets. And suppose you give me a function from f to your field K. So this f is a function on x. Then I want to obtain a function that I want to call the push forward of that function f by the map M. This should be a function on OY. What can I do for that function? Well, this should be evaluated at an element y. And I know how to evaluate my function f at elements in x. So what I'll do is I'll take the fiber. So I can do the following. I can grab M inverse of the element y. So that's an element in x. And I can evaluate my function f there. Now this is certainly not well defined, because I can take two different elements in x that map to the same point in y, and the function f might not be the same on these two elements. So what I can do is just take the sum. If the sets are finite, that sum is well defined. And I can normalize it so that it's not horrible. I'm going to divide this by the size of this set. This is just a normalization that doesn't need to be there. If the sets are finite, this makes sense. So now how can I make this more, more general than just finite sets? Well, just take compact spaces. So if x and y are compact, well, instead of this sum, I'm going to be able to integrate. I'm still on the fibers. By inverse, I keep calling this by M inverse of y, I'm going to integrate this f of M inverse of y. Oops, f of x, dx, and x is there, in M inverse of y. And this I'm going to divide by the size of this set. Now the size of that set is the integral of 1 on the same set. And this I declare to be the push forward of f, evaluated at the point 1. So now, what did I need? I didn't really need that these two spaces are compact. The only thing that I needed is that the fibers are compact, because this is where I need to integrate. So the only thing I need to do is this set, whatever it is the fiber of this map M, needs to be a set that I know how to integrate. So if the map M is proper, that happens. And this is the definition of Proper is a map is proper if the preimages of compacts are compacts. In particular, I'm in a place where points are compact sets, and I'm taking the fibers, so the preimage of a point should be compact in X. That's all I need. If the map is proper, then I have well-defined everything here, and that defines me a push-forward of functions. So for compact groups, this is always true, and I don't need to do anything. If my groups are not compact, then I want this multiplication to be proper. If my groups are not compact and the multiplication is not proper, then I need to do some kind of trick to restricting this integral to some compact subset of the preimage. However, for those groups that are there, we have this notion. An exercise, no, let's do that exercise. Let's check that that definition there coincides with this definition in the case that the group is G is finite. Okay? So in the case that the group G is finite, so if G is finite, I'm going to repeat this definition here. That's the integral, it's just a sum. Then, if I have a function f is a function in G, and if I have a function h is a function in G, I'll define the product of the two functions to be this. F star h is this. This is the convolution product. And this happens every time that you have a space with three projections to itself. This gives you a definition of a product. In the case when G is finite, that product is what? Well, is the push forward. The push forward is this sum. So I have 1 over the size of the preimage of a point. So I want to evaluate this on an element in G. And what I need is 1 over the size of the preimage of G by the multiplication. Let's do that in a second. And I'm going to sum over that preimage. So I'm looking at elements x, y in G such that x times y, because that's the multiplication map, M, is equal to G. And what I need to do is take my function, and this function here is the pullback by 1 times the pullback of the other one evaluated at that preimage. So this is f of x times h of y. Now, how many x, y's do I have in G that multiplies to G? Given 1G, for any element of the group G, x, y is fixed. It's equal to G times X inverse. So this has the size of the group. In other words, this is the usual convolution product of x in G, f of x, h of, well, y, that needs to be x inverse times G. In particular, if you take the function e g to be the characteristic function, well, evaluated at the element h to be 1 if h is G, 0 if h is not G, and you multiply two of these functions, e.g. with eh is e of G times h, which is that multiplication there. So we've seen that the algebra of functions in G for a finite set with this multiplication given by push-pull is the group algebra of G. But the group algebra is something much more general. Whenever you have a set with three projections, you get this multiplication. But that multiplication could be anything. At no point I've used any structure of the group. The theorem, which is a very simple theorem, if the map M is associative, you don't even need a unit. You only need this associativity of the map. What does associative mean? It means that, well, I'm not going to write. It's just associative. Then star is associative. So whenever you have a set with 3 projections like that, and a map M which is proper and associative, then you have an associative algebra associated to it by that construction. And the beauty of this construction is that this works in a much more general context. If instead of looking at functions, you look at vector bundles on the spaces, if these are varieties, and you look at vector bundles on the spaces, you can pull them back, tensor them, push them forward. You can do this for cohomology, you can do it for varieties that live over this, and you're going to get some new structures. This is used all over and over again. Anyways, so now we have this beast that I constructed, and lemma K of G, which now means the ring of functions on G in whatever category you are. If your group is algebraic, it's just algebraic functions on an algebraic group. This is a vector space, which is an associative algebra. This is an associative algebra. And H acts there. And H and G acts there. So I have an obvious map from G to K of G. In the case where G is finite, again, the map is you send G to multiplication by EG. For example, that works. This is obviously a group homomorphism. Okay? In the case when G is not finite, well, I've already told you what this guy is. So you know what it is. You can describe this completely geometrically in that sense. But it's good enough already when G is finite for what I wanted to do. The point is that this guy is a G module. And I can restrict the action of G to the action of H. So now, if you give me, if V is an H module, then you can just look at K of G, which comes with an action of H. So I'm going to take this tensor product and I'm going to quotient by an equivalence relation. So that equivalence relation is the following, is that for F in K of G, H in the group H, and V in the vector space V, I'm going to declare F tensor H acting on V to be equivalent to FH tensor V. So that tensor product is the same, is denoted as K of G over K of H with V. And this is a G module. Because G acts by multiplication on the left here. Actually, in this language, we can do two things. So what I've given you is this functor that goes from V to K of G tensor over K of H V. This is a functor that goes from H modules to G modules. And I also have given you another functor that goes from V to functions from G to V that satisfy star. And this is also a functor in this direction. So this functor, I'm going to, I don't know. I'm going to call this functor induction. And I've called this functor co-induction. And then I have the functor in the other direction that goes from G modules to H module that is just a restriction. I only have one functor in that direction, which is forget the action of G and remember only the action of H. So clean, I have three functors there. The two induction and co-inductions are adjoint to the restriction. But I've claimed before that if you are adjoint, and I think we've proven this by the universal property, if you have an adjoint, you have that adjoint is unique. So that means that this restriction functor from G to H has two adjoints. One, so if this guy is going to be left adjoint to one of those functors and right adjoint to the other functor. So I want you to guess which direction. I mean, it's a 50-50 chance. So one of those functors looks like it's left adjoint and the other one looks like it's right adjoint. And you should already know in which direction it goes. So I want to know, where do I put this functor, this induction functor? I've only given one example of a pair of adjoint functors, which is the home tensor adjunction. And that functor there clearly looks like tensoring with something. So that can only be right exact. And indeed, it is right exact. Tensoring with something always preserves surjections. So this functor here, which means tensoring with this guy, is right exact. Therefore, if I am claiming that these are adjoint, well, this guy better be the left adjoint. So induction is left adjoint to restriction. And the other one I'm going to claim that is co-induction. And to make it even clearer, notice that this vector space here can also be viewed as a home. So this is a home from K of G. Well, no, let's not put this equal, but I could have done this in the category of H modules. And still G acts there. So I'm going to leave that for you to think. Most probably I'm going to put this in homework. But let's analyze this adjunction that I have here. So I claim that I have an induction being left adjoint to restriction and being right adjoint to co-induction. So let's prove this. What is the statement to prove here? Well, there's no proof. I'm just going to state this. So what does this mean? This means that homomorphisms in the category of G modules from the induction of H to G of an H module V into a G module W is the same thing as homomorphism in the category of H modules from V to the restriction to H of W. And the restriction is W itself. So we need to find this isomorphism. Namely, you give me a linear map from V to W, and you want to get a map from this space which is larger than V. Notice that the induction of G to H from V is larger, is almost always strictly positive. So if H is equal to G, then this is V. But in general, when H is not G, this space contains properly V inside. For finite groups, what's the dimension of this space? So for finite groups, this vector space has dimension, the number of elements in G, times the dimension of V, but then you're kicking out the dimension of H, which is the dimension of this space. So for finite groups, this space has dimension of V times the index of H in G. And V sits inside canonically. Of course, there's an obvious map from V to here because you can send the vectors V to V tensor 1. So that's a linear map from V to this space, which is obviously an injection. So V sits inside here always, and it's almost never equal. So I want to extend the map from V to W, phi, some linear map from V to W, to a linear map from the induction to W. Okay? So what I need is to go this way. And I know the other side is obvious. If you give me a map from the induction of V to W that commutes with G, right? So you give me a map from here to W, you compose with the inclusion of V to get a map from V to W. So the map from here to here is trivial. Okay? So you give me a map from here to here, you just compose with the inclusion of V. I just gave you what the inclusion is V tensor 1. How about the other way around? If you give me a phi from V to W, how do you get a map from the induction to W? Well, let's finish with that. So if you give me a map from V to W, and now when you give me an element in the induction, this is an element F tensor V over K of H. And what you want is to give me a map to W. Any guess? That one is not entirely trivial. It cannot be trivial. Okay? But I'm claiming that there should be a way of writing this isomorphism. This should be an isomorphism of sets. So I need to find out what is the image of this guy inside of W. And what I know is how to apply phi to V, which is in W. So that's the given data is a map from V to W. Now W is a G module. So F being in K of G acts here in W. So I can do this. Is that well defined? I'll leave you to prove that this is a well-defined map. So you only need to tell me what is F acting on a vector in W. Because F is not in G, but it's in K of G. So there's a very simple lemma. I'm doing this for finite groups, but this is in general in all the categories that I said so far. There's an equivalence between G modules and K of G modules. This equivalence is very simple. If you tell me how G acts on a vector, then you obtain how K of G acts because you declare that A of G, e.g. acting on V, is equal to G times U. Conversely, if you give me how K of G acts on a vector space, then you've defined G acting on V by this equation. So that's an equivalence of categories between G modules and K of G modules. So whenever I have a module where G acts, then I know how to act by K of G, and I'm using that action. Okay, so that's induction. That's another appearance of the same tensor home adjunction we had before. So this is a tensor functor, clearly. It's tensoring with K of G over K of H. Why the restriction is a Hom functor. So if I said before that the adjoint to tensoring should be a Hom, this should be left exact because it's adjoint to is adjoint on the right to a functor. So this functor here should be left exact. And this should be a Hom, because this is a tensor. And indeed. So how do I view the functor that takes a G module W to an H module? And I want it to be a Hom functor. Well, if I look at Hom, oops. So the functor here that was this induction was tensoring with K of G over K of H. So what is a Hom? So you give me a G module W, and I want to get an H module. And I want to view it as a Hom. And I want to view this as a Hom applied to W. So I already know that these are maps to W. And most importantly, I want to get that the space should be W, because the restriction of V of W is just W itself as an H module. So whatever I write there should be a vector space that is isomorphic to W itself. So for our modules, what I did is I took the tensor functor of something was adjoint to Hom from that something. Now the problem is that for our modules, I was going from our modules to itself. Now these are two adjoint functors in different categories. Well, what you can do is either take K of G and take the modules over K of G. And that's well defined whenever you tell me 1. Where 1 goes, it goes to W. So this is isomorphic to W. Or you can just take Homs from K of H. But the problem is that I haven't told you how K of H, G does not act there. So K of H acts here. But I haven't told you how K of H acts on W. But of course, this is going to be isomorphic. But this I have told you. I've told you how G acts here, told you how G acts there. So I can take Homs like this. This space is isomorphic to W. But this space also carries an obvious action of H, because H acts on K of G. So that's the restriction. And that's the Hom tensor adjunction again. So that's why induction and restriction are adjoint. On the other hand, restriction is exact. Restriction is not only left exact, it's exact. Clearly, if I have a sequence V to W to Z, and I view the same sequence as H modules, it's still exact. So restriction is preserving both exactness, both kernels and co-kernels. And this is because not only is a right adjoint of something, but it's also a left adjoint of co-induction. So I'll leave you to prove that these two guys are adjoint. And that's why restriction is exact, because it has both adjunctions on both sides. Now, of course, for finite groups, induction and co-inductions are the same. So for finite groups, you have natural isomorphisms between this, and this is essentially because K of G is naturally isomorphic to its dual. You have a natural map, which is an isomorphism between functions in G to the group algebra of G that takes EG to the characteristic function on G. So those two are the same. But for groups that are not finite, these two are different. And induction and co-induction are not the same thing. Okay, so we spent a lot of time just giving examples of different functors and why exactness on both sides. So let's prove that statement about exactness. And And why is it that I'm talking about exactness? Well, actually, let me just move to the next topic. Which is I would want to start talking about resolution of objects and how to compute homologies of objects by applying a functor to the resolutions of those objects. So, yeah. So let me. We're going to have time. Not sure if we're going to have time. So this is the model of what we want to do. I think I've defined only one homology theory so far, that is homology of Lie algebras. So since I've only defined one homology theory, I'm going to use that homology theory to give one example. So Lie algebra homology. And this is what we're going to be applying all the time now. Lie algebra homology, or cohomology, but the complex I've defined was the Chevalier-Eilenberg complex of a Lie algebra. And this was and we've written explicitly what the differential was. Okay. So where does this complex come from? So, given a Lie algebra, there's an associative algebra. It's called the universal enveloping Lie algebra. And just the same as for groups, that G modules are the same thing as K of G modules. For Lie algebras, you have that G modules are the same thing as U of G modules. If you like Lie groups, these are distributions support that the identity of the group. You can look at left invariant differential operators on the Lie group. That gives you this. Otherwise, just take the following associative algebra with a universal property. For any associative algebra, remember that if A was associative, we obtain a Lie algebra, which is the same vector space, with the bracket being the commutator. Oops. Whenever you have an associative algebra, we've seen this, that this guy is a Lie algebra. So any associative algebra is a Lie algebra with this bracket. So the universe, an enveloping algebra A for a Lie algebra G is an associative algebra with a map of Lie algebras from G to A Lie. That's what an enveloping algebra is. Now, a universal enveloping algebra is universal for this property, meaning that G comes with a map to U of G, a map of Lie algebras, and whenever you have any other enveloping algebra, then this guy exists and is unique. So the trick is to prove that this guy exists. And it does. We might prove it later. But this is an associative algebra that is generated and is freely generated by G. That's the whole point of being universal. It has G inside and is freely generated by G, with the condition that the bracket in this guy is the product, is a commutator, and it has to coincide with the bracket in G by the fact that this is a Lie algebra amorphous. So now every time that you have a module for this guy, it becomes a module over G by just restriction. The other way around is not entirely trivial, but we can do this in a future class. The point is that now I have U of G as a U of G module with the multiplication itself. So this, therefore, is a G module. And we can tensor this complex, or a complex that looks like this is vector space, with U of G. And this is known as the Cos-Joule resolution. So let me call this K. The theorem is this complex, so this continues forever. I'm going to put this in degree 0, this in degree 1, and I'm going to stop here. So this is not part of this complex. Now, or if you wish, if you put this as part of the complex is exact. If you put this as part of the complex is exact. If you don't put it, then this complex has homology in only one space. So the homology of this complex, let me put A, it's only non-zero when I is equal to 0, and in that case, it's just U of G. So this is going to be known as the projective resolution of U of G. And whenever you have that situation, that I'm going to give you one in a second for associative algebras, what you can do is, whenever you have this situation, and you give me a G module M, therefore it is a U of G module, what you can do is tensor this complex K, tensor over U of G with M. Now, how does this guy look like? Now, what? I need to tensor this thing over U of G with M. And I need to tensor this over U of G with M. For all of them. So now, as vector spaces, since I am tensoring this over U of G with M, this is just G tensor M. This is wedge 2 of G tensor M. And so forth. This is wedge K of G tensor M. And this is the complex that I gave, computing the Lie algebra homology of G with coefficients in M. So the homology of this complex here, which is K tensor over U of G with M, is the Lie algebra homology of G with coefficients in M that I defined before. So let's do this for associative algebras, because it's easier, and I can do this in 5 minutes, and then I'll stop. But I want to prove. So it's not entirely trivial, and it requires some work to prove that this guy is exact. But for associative algebras, it's absolutely trivial. So let A be an associative algebra. Unital algebra over a field K. And let me construct the following complex. So this is going to be the next toy example for homology. So what is the differential here? If you give me an element A0 tensor A1 up to AN, and you apply the differential of this, well, this goes from A tensor n plus 1 to AN. And the differential is the only thing that you can, well, the only thing I can think of, which is the sum of minus 1 to the I, A0. Now in the position I, instead of putting I, you put I times AI plus 1. So you multiply two elements, two consecutive elements, and you end up in AN. So I claim that this complex is exact. It doesn't have any homology. Let's prove that. I claim that this complex does not have any homology. And to do this, I'm going to explicitly construct a splitting. So this is a split exact complex. Okay? So what we'll do is we'll find a map from AK to AK plus 1. And it's the only map that you can think of. So if I want to find a map from k elements on A to k plus 1 elements on A. And the only thing I can think of is just add one element, it needs to be the 1. Or I add 0 or I add 1. So let me write S to be, let me write like this, A tensor k plus 1 to A tensor k to A tensor k minus 1. Here is D, and S goes in this direction to A tensor k plus 1. And it grabs A1 tensor A k, so that's k elements, and it gives me back, and I reserve the right to again put this 1 in the wrong position, but I'm going to put it here. 1 A1 AK. So that's going to be S. So let's apply D and take D and S, and then we stop right there. Okay, so this is S, this is D, and I want to compute D squared. Okay, so I just told you what S is. Let's apply D to this. And D applied to this is 1 times A1, which is A1 up to AK. Plus, and now I'm going to start at this point. A1 times A2, but that comes with a minus 1. And then A2 times A3, and that comes with a plus 1. So this is the sum of minus 1 to the I. Well, I start with 1. AI times AI plus 1. And then I end up with AK. Okay, so that's D of. It has two. Is this plus this sum? How about the other way around? Let's do D first and then S. So when I do D of this, I have minus 1 to the I. But now I need to be careful because I started here with 0. So 0 was with a plus sign. Now I'm starting with 1. So 1 should be with a plus sign. So this is I plus 1. And I have A1 up to AI plus 1, AN. And now I apply S to that. So when I apply S to this, what do I get? Well, I'm going to add a 1. The first term here comes with 1, A1. That has a 1 plus 1 is 2, so it has with a plus sign. And I add the 1, I end up having 1 tensor. What did I do wrong? Well, 1 tensor, A1. No, the first term here is A1 times A2. It doesn't matter. It's just this sum. It's minus 1 to the I plus 1 of 1 tensor AI plus 1 AN. And I think here is where I messed up. When I took D of this, is 1 times A1, which is this term. All the other terms still have the 1. So this term and this term have different signs. This is minus 1 to the I, and this is minus 1 to the I plus 1. So SD plus DS applied to the element A1 up to AK, tensor AK, is A1 up to tensor AK. So this plus this is the identity. Therefore, the identity is null homotopic. Therefore, the identity induces 0 in homology. So the homology has to be 0. So this is a split exact complex. Let's stop right here. I'm going to take this complex. So I'm going to remove this A. I'm going to put this in degree 0, this in degree 1, and so forth. And this complex is going to be called B of A. And the homology of B of A is only concentrated in degree 0. So this is the same situation that we have there. Now it's just that we prove this rigorously. So this is delta I0, and it's A in degree 0. So that's the bar complex of A. And definition theorem. B of A is a complex of AA by modules, namely on each one of these elements, I have a multiplication of A on the left and of A on the right factor, and this differential commutes with that. If I multiply A0 by anything, stays there. If I multiply AN by anything, stays there. Of course, in the middle, I cannot multiply by anything because the differential screws that up. But the first and last factors are there. So every element here carries a multiplication of A on the left, a multiplication of A on the right, and the differential commutes with that. So this is a complex of AA by modules. And given any guy with a multiplication of A on one side and on A on the other side, what I can do is tensor it with B of A. Over AA. Namely, this is an equivalence relation where the multiplication on the left here is sent to the multiplication on the left here, and the multiplication on the right here is sent to the multiplication on the right here. Now this is a complex of vector spaces. I take the homology of this, and this is the Hochschild homology of A. This is the definition, with coefficients in A. So that gave us 2 examples of homology. Next class, I'm going to talk about projective resolutions. I'm going to prove that this is a projective resolution in the category of AA by modules. And I'm going to start talking about derived functors. So now we have at least two examples to talk explicitly about derived functors for these representations.